It's a pleasure to have Abigail Ward from MIT, and she will talk about symplectomorphisms mirror to birational transformations of P2. Okay.
Great.
Is there any chance we can make it a little bigger?
Make it well. So I'm going to yeah. So just to note on how I'm going to do this, I'm going to kind of do it like slides. So I'll try to just like kind of do part of the screen at a time, which I think should be big enough. If that big enough.
Can you turn it sideways by any chance? No.
No, because if I turn it sideways, it won't let me show 2 pages at a time. Is the problem, and I need to be able to do that. So, okay. But sorry. Yeah, I'll try to yeah. It sounds like maybe this has worked better in other situations than it will now, but if you guys need to please just yell at me if you want to see more of the screen at a time or something like that, or less if you need me to zoom in. But yeah, so technical remarks aside, yeah, I guess I'll get started. So thank you very much to the organizers for the invitation to speak. I'm going to talk about some joint work, which is in progress with Elsa Keating. I think everything I'll talk about today is more or less good, complete. And then there's some stuff that we're trying to add, which I'll mention as I go along. But right, so just some background and conventions. So I've tried to adapt this talk to the audience. I apologize, I haven't been able to attend very much of the summer school or the talks yesterday. So a lot of this might be sort of repeats, but I just want to kind of get people on the same page. So, okay, so now let me see if I can kind of zoom in here. So, okay, so this is probably a bit small, but it's okay because I think you all should sort of expect this anyway. So here in this talk, Y comma D is always going to denote a Lewinga pair with maximally degenerate boundary. So D is an anti-canonical divisor, and D is a cycle of P1. So, and then U is going to be the complement of D in Y, and U. I'm going to fix a holomorphic volume form, a non-vanishing. Sorry, I'll write that a non-vanishing holomorphic volume form. With simple poles along D. So that's going to be called capital omega. So capital omega witnesses the fact that YD is a log Calabi-Yau pair. And of course, the simplest example here is maybe your favorite toric variety. So you can think about P2, comma, this triangle of lines at infinity. And omega here, written in affine coordinates, is dx dy over xy. Let me also just note that since there are experts in the room, this same omega here will work on any YD after choosing a toric model. So, oops. Or any YD after choice.
I don't think you're seeing what you're writing.
You're not seeing what I'm writing. Oh, damn. Okay.
Because of me, man.
Is it not working? It's not working. Yeah.
It's
okay.
Working. It just had zoomed in to see better, and
that's all it's done. Okay. Yeah. Sorry. Let me just try to reconnect this.
No, it's all good. It's all good. It was just something from our side. We zoomed in to a particular place in the paper to see better, but now we see. Now we're good.
Okay. So yeah. So unfortunately, the connection, this cord is sort of having some problems. So let me see if I can. I mean, it doesn't really matter for this part here, but I would like to do some writing later. So, okay. Is it working? Yes. You see me scrolling? Yeah. Okay. Yes. Okay. So hopefully it just works. But let me know if it disconnects again. There's a lot of kind of moving parts because I'm traveling, so the technology is a little bit iffy. But okay. So right. So So I have this holomorphic volume form on my open log Lebesgue surface. And in this talk, I'm going to always consider YD distinguished in its deformation class. So you can think about this as saying, like, if you like, you have a short exact sequence of mixed Hodge structures, so 0 to something like H. Oops. Sorry.
So this was covered a little bit in one of the talks. So if you want, you can assume that we know this distinguished.
Okay. Well, let me write the third term here, and then I'll speed up.
No, don't take this as speeding up just because it wasn't in your slide. So I wanted to don't speed up. Slow is good.
Okay, so this splits as a mixed Hodge structures. But you also will know that this means that YD has an exact mirror. So this is the work in the work of Hacking and Keating that this thing has an exact mirror. So now let me move on to that work. And I was meant to summarize it a little bit, so I'll try to do my best. Okay, so there's two papers, right? So in 2020, they constructed, so given this data of a YD, they constructed some symplectic form manifold with an exact symplectic form, along with a Lefschetz vibration, such that the derived category of Y is quasi-isomorphic to the derived Fukaya-Seidel category associated to the Lefschetz vibration, and the derived category of U, so the open log Lebesgue surface, is quasi-isomorphic to the derived Rat Fukaya category. And then I was just going to say a little bit about how this goes. So what you do is you, sorry, I'm like trying to figure out the best way to arrange everything on this desk. So what you do is you find a full exceptional collection of line bundles on Y, and then you construct a Lefschetz vibration, so you sort of by hand. So you match with some thimbles of a Lefschetz vibration. So the picture always looks something like, maybe like, this is how you would draw it. So I'll just maybe do a little cartoon version. I'm going to distinguish that guy. So you pick some paths in the base, and you say, okay, I have critical points over those values, and then I draw a fiber here, which I know this is now like probably really small, but I just want to do one example. Okay, that's like the ugliest thing I've ever drawn, but somehow like this would be an example of the cartoon for the blow up of P2 at one interior point. And the point here is that the fiber here has a number of punctures, the same number as punctures as the components of D. So in this case, it has 3 punctures, and then you attach extra thimbles along some choice of cycles in that fiber. All right, I'm not an expert on the work of Hacking and Keating, but that's sort of more or less how it goes. Like it goes through this Lefschetz vibration machinery, and you use work of Giroux and Pardon, I think, to say, okay, I can construct a form manifold in that way. So that's paper 1. And then their second paper, so they exhibited a map. See, is this correctly scrolling? Yeah. So they exhibited a map from the automorphism group of your YD to pi naught of the compactly supported. So let me say this. This is compactly supported symplectomorphisms. So that's what that subscript C means. Compactly supported symplectomorphisms of M, which respects the HMS equivalence, meaning, okay, so it matches up the induced autoequivalences of the derived categories. And so how does this go? Okay, well, so now you use some machinery of mutations of left-shift vibrations. This is kind of stuff that Elsa is really, really good at. She's good at a lot of things, but among them is this. So you let me again draw like a really terrible little cartoon, just to give you an example here. So this would be, so say you were looking at, well, let me just draw this first. Orange is my kind of distinguished color there. Let me draw this and then I'll tell you what's happening. So this is supposed to sort of, oops. This is maybe an example of this is mirror to P1 times P1. And these, you should imagine these four thimbles here as sort of corresponding to, well, this is not quite right, but essentially they should match up with the four components of your divisor D and P1 times P1 as a toric variety. And then, so P1 times P1, you can sort of like think about rotating the fan by 90 degrees, or maybe by this matrix 0, 1, negative 1, 0. That gives you an automorphism of your YD, which you can get at by performing mutation here. So this guy kind of moves to the top, and so that sort of cycles through your components. Sorry, cycles your components through this rotation here. And now I should tell you that I'm sort of lying because it's hard to give an actual example of this map here. Because why is that? Because this automorphisms of YD, I demand that they respect, or maybe, sorry, preserve the point-wise.
Can I suggest a convention? When you write something, maybe you can try to keep it at the center of the, so that we can zoom in, because we have to zoom out and then that becomes really small. So
I see.
When you write something, try to put that kind of towards the top of the page so that when we zoom in, we can still see it. Is that possible?
Yes, let me try to do that to come. But this was all sort of background, so I don't want to like get too, but yes, I will try to do that. Yeah, sorry.
No, it's not, obviously not.
Yeah, and then the other thing I kind of just want to say about this slide is I really will not use this description as a Lefschetz vibration throughout the entire rest of the talk. I just wanted to kind of have it on the board because I think I'm the sort of closest representative to the Hacking Keating school, maybe at this conference. So I wanted to give you guys an idea of how this is done. But if you don't like these Lefschetz vibrations, or if you don't really want to think about them, then you're totally fine to not do so. But this is the background. So now let me move on to my work with Elsa. So let's see. So can you see? So sorry. So I just don't know what's like on the screen in that room. So
perfectly the page up, like you know how there are two pages.
Yeah.
We can see that perfectly, like from 2021 until.
Oh, I see, but you can't really see this motivation thing. Okay, so I should like go like that or something.
Yes.
Can you?
Perfect.
Okay.
A little bit more up.
Okay.
Yes.
Okay. Okay. All right. Yeah. Just let me. Sorry. So I have no idea what's happening on that screen in that room. Then I have truly no idea. So just tell me if like, yeah. Well, it has to be a negotiation as to what I show when. But okay. So the motivation for my work with Elsa is we want to find. I mean, the first motivating question that we had was the question of if you could find a mere correspondence between the automorphisms of the open log Clavier surface U and the symplectomorphisms of M. And then now let me say that this So you don't expect compact support for these symplectomorphisms. So previously, you considered only automorphisms of YD that fix D pointwise, and then that should sort of be mirror, maybe under SYZ mirror symmetry, I don't know, to symplectomorphisms which are compactly supported. So now if you consider all automorphisms of U, you should sort of be acting at infinity in some way. And so you no longer expect compact support for your symplectomorphisms. So you need to make sure that whatever symplectomorphisms you construct actually act on the Fukaya category in question. Obviously, like a compactly supported symplectomorphism will automatically preserve whatever boundary conditions you have to have your Fukaya-Saito category or your wrapped category. Here, you need to do some work to make sure that you're preserving those boundary conditions in order to, well, okay, I mean, in order to get something that matches under mirror symmetry, right? Like the idea is that you want to have something which matches up autoequivalences. So it better act on both sides. And then the other thing I want to just point out for you guys is that this group can be like a priori, this group is not necessarily finite. So previously the automorphisms of YD are finite necessarily, but this can be a group of infinite order. So those are sort of two two features that will appear. The second source of motivation is to find a mirror correspondence between this group of birational transformations of P2, which preserve omega. Sorry, so this is not, it's not an honest error, it's birational error. And you might want to match those up with the symplectomorphisms of something. But now the question is, okay, that's why I have a question mark, like what is this something? It's not clear. And I'll connect those two motivations below. But what I will first need to do is to define for you guys, okay, so I have the entire group of birational the birational transformations of P2 preserving omega. And I'm going to define a distinguished subgroup. So this is the Bir sub E subgroup here. And so this is a distinguished subgroup, and it is isomorphic to pi naught of the original subgroup. So somehow this Bir P2 thing, or let me say this. So this distinguished subgroup picks out the connected components of the bigger group up there. Okay.
May I ask a question? Can you
yeah,
hear
of
me?
course. Of course.
Do you require this to somehow fix U?
The
birational automorphism?
So we'll see that the fact that it preserves omega automatically means it preserves U.
Because it's polar locus, okay.
Yeah, exactly. Because omega is sort of picking out D, right? Yeah. So, yeah.
What's your precise assumption on D? I mean, you put some components where omega does not have poles.
So I demand, let's see, I think the way that I will construct my omega and my YD, that won't happen. So I will always have, yeah, indeed. I think you could say, okay, well, I have a holomorphic volume form on this U that doesn't have simple poles along all components of D. But when I work with the toric models, like I will always have poles along each component of D. And sorry, I'm not very good at kind of doing algebraic geometry during live during talks, but I
okay,
think,
I think it's fine. Okay.
Thanks. Okay. Yeah. Sorry. Let me come back to that question. But right. So omega will always have simple poles along D. Yeah. And so that will imply that it preserves U. Other questions? All right. So let me continue. So now if I, so now can you guys see this like commutative diagram part of the board? Yeah?
Yes.
Okay, great. Okay, so given such a phi in P2 comma omega, the indeterminacy locus of phi is going to be within that D. So the divisor D. And so what this will imply is that there exists yi, a pair of yd, so that you have an honest biholomorphism between the y1 and y2. So there exists such a diagram like so. So you have your phi here, mapping between your algebraic torus, the C star squared, and now you've blown up the indeterminacy locus, points in the indeterminacy locus of phi, so that you have an honest biholomorph. So this is let me just say some words about this map. So this is a biholomorphism and we also know that it sends D1 to D2. So and what I also want to say is, okay, so note that this is not unique, sort of evidently, because I could do further blowups. So if I took like such a pair like this, okay, now it's going to get kind of sloppy because I didn't leave myself quite enough room here. But I could take such a pair y1, y2, where you've resolved the singularities of your phi, and then you say, okay, well, I'm going to maybe blow up another point on my D on y1. Okay, well, if I blow up the image of that point under my phi bar, then I have a new phi bar extending this birational transformation on the blowups, right? So really you should think about sort of towers of compactifications of C star squared. And now let me tell you why I'm sort of working with this this distinguished subgroup beer sub E. It's because if phi lives within that distinguished subgroup, then the yi that you consider can be taken to have the distinguished complex structure. So you can actually run mirror symmetry, or rather we know how to run homological mirror symmetry for those. We're also thinking, well, the part that's really in progress in this project is sort of the full birational group. So maybe I'll say a tiny bit about that at the end. But for this talk, I'm just going to consider phi in this distinguished subgroup, which corresponds to the to allowing yourself to have these resolutions of phi using the distinguished yi. So now let me just do some examples just to orient us. So the examples, okay, so like say I could take like x, y maps to 1 over x, 1 over y. And again, I'm going to kind of use a suggestive notation here, like -1, 0, 0, -1. And so, okay, so this map doesn't extend to a biholomorphism of P2 to P2, but it does if I consider not P2 times, sorry, P2, but P1 times P1. So this defines an automorphism of P1 times P1. And okay, so that's sort of one source of phi in this distinguished subgroup, is kind of elements in SL2Z, and the other main source, or the other source is a cluster transformation. So I could take like x, y maps to, so this is going to be my cluster transformation I'm going to consider throughout the talk. X, y maps to x, y over 1 plus x. So I think everybody in this room knows that this maps some blow up at let's see, blow up of P1 times P1. So at -1, 0, right? I have to blow up the point -1, 0 to have a well-defined coordinate on the right side there of P1 times P1. And then it maps it to another blow up of another toric variety. So I think -1 infinity of here's a brick surface, right? And if I do this in terms of, I'm going to now start using some what I would call maybe like an enhanced fan notation or something like this. So this is this diagram on the left here, and I'll talk about this, but this diagram on the left here represents this blow up of P1 times P1, and then it sends it to, let's see, this guy on the right here, which represents the blow up of F1. Yeah, questions.
Can you scroll up?
Can I scroll up? Yeah. Is that better?
Yes.
Perfect. Yeah.
Okay, so I just should have it at the top. Got it. All right. Yeah. Okay, other questions on this before I continue? Cool. All right, so now let me tell you about the mirror symmetry that I'm going to use for this talk, or sort of how I actually think about these mirror correspondences. So let me now scroll up to this part. So so now you guys can read this explicit toric models to almost toric vibrations part, I think. Yeah. So what we do is we can say, okay, well, given a YC, so now, sorry, I've now started to go too fast. So let me slow down a little bit. So I can index all the possible sorry, let me start over one more time. So given a YC, sorry, given a pair Y comma D, let's just say it like that, I know by work of GHK that I can express it in terms of some interior blowups, in terms of blowing up some points on the interior parts of your divisor D for some toric variety, and some blowdowns too, but that doesn't actually matter for me. So I'm only going to consider YC, where I can get it by just doing some blowups on interior points of your divisor DT. So YT is a toric divisor, and then DT is equal to the toric boundary. And so now now I say if I choose an embedding of C star squared into YT, so I no longer kind of consider as an abstract toric variety, but I really choose an embedding of the algebraic torus, which kind of corresponds, right, to choosing an embedding of your fan into R2. Then if I choose such an embedding, then I get a diagram like so. And what I also get is, so this determines a map from the automorphisms of UC into the birational transformations of P2, right? So I told you these sort of two sources of motivations, and how one implied the other, or sort of one naturally leads the other. This is sort of the converse. So I can study the automorphism groups of these open surfaces by thinking about subgroups of the birational transformation group. Okay, so I take this data here, and now I call this an explicit toric model for my YC, and now I can form this set here where I've indexed all the YC Y sub C C's by this indexing set CY2, which, so this you should think about as this is the set of log Calabi-Yau surfaces with an explicit toric model. So with a diagram like that on the left. And now the observation is that this set is partially ordered under blowup. So what I mean by that is that if I have, say, Xi prime greater than Xi in this partial ordering, then then I can obtain YC from doing blowups of point I can obtain YC prime from blowing up points of YC. So what that'll do then is that'll give me a map. Let's see, from, get my arrows right, from the derived category of YC prime map going that way, right, on the derived categories of the closed surfaces. But what it also tells me is, okay, so now I have an inclusion of the open log Calabi-Yau surface UC into the open log Calabi-Yau surface UC prime. And so I have a map. Okay, let's say I have a map going the other way. Sorry if you can hear that. I'm like in front of a port, so you can hear the ferries sometimes. UC, sorry. Okay, let me just get this right. Sorry, this is now very sloppy. But okay, so you have these maps between your derived categories, and I have this system of log Calabi-Yau surfaces. And so the other thing that I just want to say right here is that the these blow up operations blow up on D, or rather on your set of Ds. But I can do both corner blowups and interior blowups here. So for example, if I took a toric variety and I blew up one of the corners of my toric boundary, so now I have a new boundary divisor with a new component, right? And I would say that new pair YD lives above the previous one. So I can do both interior blowups and corner blowups. Sorry, I know I'm like kind of belaboring all of these points here, but you should, this is sort of the basis for the rest of the talk. So it's good to kind of get it straight. Okay, so I have this data. And now I can use this data to construct or to sort of visualize my mirrors to the log Calabi-Yau surfaces and also sort of fit them together into a directed system. So how do I do that? So now let me, okay, yeah. And I apologize to the people who are like watching on Zoom, because I think now you're like kind of getting spoilers for the rest of the talk. But it's good to have the people in the room be able to read the writing. So if you can read ahead, apologies. But okay, so now I'm going to use this data to construct my mirrors. So given a YC, DXC, I construct this mirror in C as an almost toric vibration over the base, over some base BXC. So this is an alternate, let me just note that this is an alternate description of the Hacking-Keating mirror. So they run their mirror symmetry through Lefschetz vibration, as I said, but you could also visualize the underlying manifold in terms of these almost toric vibrations. And so this, I think, again, you guys are all expert on these integral affine structures, so let me not spend too much time here. But what you do is, okay, so you start with the fan for your toric model. So the toric variety, sorry, let me quickly scroll back up. So this toric variety YT, you had this YT here. So you start with the fan for YT along with its explicit embedding in R squared that you get from this explicit toric mod of theta. And now you take that fan and then you write it like in R2, and then you record your interior blowups that you did to obtain your YC by these dashes here. So I already sort of used this notation, and hopefully, you guys have, this makes a lot of sense to you. So I already sort of used this notation earlier in the talk. But now, okay, so we know that we can read off some Lagrangian torus vibration on my interior of my Luinga pair from such a diagram. And so what I want to do is sort of just do SYZ or mirror symmetry to get the mirror. So I never say this remark when I'm normally giving the talk. So that's why I haven't written anything about it. But that's what's happening here is I sort of start with the Lagrangian torus vibration, not a special Lagrangian one, but just the torus vibration on your interior to your log Calabi-Yau surface, and then you SYZ dualize. But you know, if you don't want to think about that, whatever. What you can think about is I'm just building some space BC, and so this has a integral affine structure with singularities, so codimension 2 singularities. And I don't think any of you are surprised by this, but I can construct this space and its integral affine structure by these diagrams here. So I say, okay, the complement of my x's is going to be the smooth locus of my base, and that's going to have a lattice bundle living within the cotangent bundle over that smooth locus. And so now let me, okay. So the problem is somehow when I give this talk, no one is ever going to catch me up. Unlike you, I want the matrix or its transpose, but now I'm speaking to a room of people who could catch me up. So whatever monodromy you think I should put around here is like absolutely the right one. I think if I'm writing down the monodromy on the tangent bundle, I can write it as something like this. And then I dualize to get the monodromy of this lattice bundle associated to the cotangent bundle. And so what's happening is that the invariant directions, let me write it like this. So the invariant directions of the monodromy on T, B, C naught are recorded by the rays of the fan. So if you like these slit diagrams, you can say, okay, I have a slit kind of going out this way on the tangent bundle, and then I need to dualize for the cotangent bundle. And now I can use work of Symington, I guess, so this is, oops, put the arrow here. Work of Symington to say, okay, well, I can take my a symplectic space where I take the cotangent bundle and I quotient out by this lattice bundle, and just put the standard symplectic form on that space, so inherited from this description as a cotangent bundle. So that has a Lagrangian torus vibration, and now I want to compactify that Lagrangian torus vibration with some nodal tori. So, you know, topologically, what's happening is just sort of like the Dane twist that you see maybe in a Lefschetz vibration, right, where you go around a singularity. But now this is all happening on the Lagrangian torus vibration side. And now the key point somehow is that if I had this relation in my indexing set of log Calabi-Yau surfaces, so this would say that YXC prime can be obtained from blowing up YXC, then I get an inclusion of Weinstein. So this is inclusion of Weinstein domains from MC into MC prime, and that you should sort of imagine as being the mirror to the inclusion of the open log Calabi-Yau surfaces.
So maybe it's good to say partially compactifies, because I think there are
Yeah, you're right. You're right. You're right. Yep. Partially compactifies. Yeah. I mean, this thing is still infinite. Yeah. But I filled in, the point is I filled in I've put these nodal tori over the singular locus of my integral affine base. Okay. Other questions or comments? Okay. So great. So now you can probably kind of guess what, or maybe you have like an idea of what I'm going to do. So now let me pull up the theorem. Okay. So the problem is the theorem takes the whole page. So I should have written it smaller somehow. But okay. So let me read off this theorem. So our theorem says that there exists some non-finite type Weinstein 4 manifold, which we're going to call M sub univ. So that stands for M universal, such that all of the log-Calabi-Yau, the mirrors to log-Calabi-Yau surfaces, so these MCs include into M universal as Weinstein subdomains. And then furthermore, so there's an injective map from the birational, from this Beer sub E subgroup into the symplectomorphism group of this M universal, quotiented out by compactly supported Hamiltonian isotopy. And let me just say, I've put this L here to just sort of indicate how to say. This L stands for Liouville, and what it's indicating is that these symplectomorphisms with this M univ preserve or act on the Fukaya category. And I can say more about the technical details then, but I don't think there's too many symplectic geometers in the audience, so let me just leave it like that. But yeah, right. So you have an injective map from this group Beer sub E to this symplectomorphism group, quotiented out by again compactly supported Hamiltonian isotopies. And now let me continue scrolling up. And now the point is that for all of your log-Calabi-Yau surfaces indexed by this set CY2, there's a map essentially from their automorphism group, but really because some of them have kind of too many automorphisms, you want to consider this aught sub E, U, comma, omega. And what you should just think is that that's your automorphism group of U intersected with your distinguished subgroup of Beer sub E, P2 minus, comma, omega. As soon as you do enough blowups, it just agrees with the automorphism group. But okay, but there's a map from that sort of restricted automorphism group to your symplectomorphisms of your MC, again modded out by compactly supported Hamiltonian isotopy, so that this map is this is induced by restriction. Let me just scroll up a little bit. So you have this inclusion of Weinstein subdomains. So if I have a map in this automorphism group, well, I know that in particular it's a birational transformation of P2. You know, it's in this group that we're considering. So it acts on this M universal. But now the point is that it actually the mere symplectomorphism is actually going to preserve this Weinstein subdomain, this MC, and so you can actually just get a symplectomorphism on that MC by restricting sort of your symplectomorphism on the big guy. And moreover, okay, so now this map here behaves the way you would expect under mirror symmetry, right? Oops, and this should actually be, I got this wrong. This should be phi. It's also a lower star hat. So the point is that this thing is going to send phi to phi hat, and the induced autoequivalences of your derived category agree. So what you've done here is you've found a way to sort of understand all of these automorphism groups, or essentially everything in these automorphism groups, all at once, and sort of this way you've patched them all nicely together. So if I'm giving this talk to like an audience of symplectic geometers, like one selling point is just like, okay, I found out, like I've produced a lot of symplectomorphisms of 4 manifolds, and moreover sort of had them all talk to each other in the way that you expect that they all talk to each other, because they really all live within this larger group. their mirrors kind of all live within this larger group, say. All right, sorry, that's a lot of talking. Maybe let me just kind of shut up and let you guys ask any questions you have on this theorem before I go on.
I have a question about like the group on the right that it maps into. L MC mod this equivalence. Is that a discrete group?
This group here, the simp sub L thing?
Yeah, so yeah.
Is this Phil that I'm talking to?
Yeah.
Hi, Phil. So I think the way that I've set up this theorem, so I'll tell you why I'm hesitating. So I think the way that I set up this theorem here, it might be a discrete group. I mean, certainly like the left-hand group is a discrete group. So the right-hand group, you're going to end up in a discrete subgroup. I think that really the right group on the right-hand side is something like, it shouldn't be a discrete group. But the way, okay, sorry, this is like the most useless answer in the world. The way I've written this might be a discrete group. I'm actually not sure if people know if like these symplectomorphisms which preserve the Liouville structure are discrete. But the group that you actually want to be mapping to, which I would say is the group of symplectomorphisms preserving the monomial admissible structure, which you guys will hear about from Andrew Hanlon later today. That group is not discrete. And in sort of the work we're doing right now on the non-exact, on the full group of birational transformations corresponding to like allowing non-exact mirrors, that the right-hand group will not be discrete. Sorry, that was an incredibly convoluted answer. But I hope, I think that the answer is like morally it shouldn't be a discrete group. Yeah. Other questions? Okay, great. So let me go on. So the idea of the proof is as follows. So M universal, so it admits a description as an anomalous toric vibration with infinitely many singular fibers. So you have one singular fiber. So infinitely many singular fibers, and they're indexed by Z2 minus the origin. So essentially, you consider all possible fans for all toric varieties. So you have array for every primitive element in Z2. You have array for every element of every primitive element of Z2, and then you also have infinitely many blowups, like countably many blowups on each of those rays. It's what's happening on the B side. So you have a base diagram that looks like this, and now you can see that the base of my almost toric vibration for the MCs, so that base includes into this B universal for all XC. So here pictured is sort of like maybe the base for let me draw it like, well, okay, let me draw it like this. The base for P1, where I've blown up once at an interior point of each of the boundary divisors. So that's the, let me make this arrow kind of actually extend into the pink region. That's this pink region here. But you can see that I could draw a similar sort of inclusion for any of my log Calabi-Yau surfaces. And then that will induce an inclusion of Weinstein domains. So. Okay, and now I will finally tell you, well, okay, so I have to scroll up, or sorry, I have to scroll down for the people in the room. So just sort of memorize that picture if you can. And now I'll tell you about the this mysterious group of birational transformations. So may
I ask something for the previous thing?
Yeah.
This lattice, so that's the position of the singular fibers. That seems unnatural to me. Is that just a choice because it's convenient?
In what sense does it seem unnatural to you?
Well, integrality of the singular fibers don't really, I mean, why?
It's a convenient, yeah, I think, well, okay, so hopefully you agree that I should sort of have infinitely many nodes on on every raise, right? So now it is a convenient choice because you can see very easily how the generators will act. I agree that sort of under SYZ neosymmetry, this is not convenient at all. Or sorry,
so the invariant directions are the rays.
The invariant directions are the rays. Yeah, sorry.
I see.
So
So that's just a way to get all the okay.
Yeah, exactly. So sorry. So right. So the invariant directions, maybe I should write that. So well, yeah. So
it's indicated in the pictures you dotted lines.
Yeah, but that's a great point. So thank you for helping me emphasize it. Right. So the invariant directions are given by the outward pointing, or well, the way the inward point. Sorry, the invariant directions are given by the rays that these nodes lie on. I apologize, I switched from like x's to dots here, and right, and you have infinitely many nodes on each ray. Okay, so and now hopefully with the next kind of thing I'll talk about, you can see why I want to actually use put in more symmetry as I did, or sort of use the actual choice of Z2 minus the origin for the location of the singular fibers. So you have a description of this group of volume preserving birational transformations of P2 by Blanc in a paper from 2013. So the group is generated, there's some relations, but the group is generated by SL2Z, so acting on the algebraic torus in the way I've sort of indicated previously in the talk. C star squared, so that acts by scaling on the algebraic torus. So this part here preserves like the C star squared sitting inside of P2, if you like. But then you also have this cluster transformation P, and that doesn't preserve the algebraic torus. So this is the only things you have to understand for this beer P2 comma omega. And then for my discrete subgroup, well, I get rid of, this is the part that's sort of giving me moduli, if you like. So I get rid of that part. And I end up with this group generated by just SL2Z and P. So there's sort of a reason that I was only working with, as examples, sort of only working with those generators previously in the talk. And now the point is that SL2Z acts on this B universal sort of in the obvious way, right? And that actually is where I'm using the fact that the nodal fibers lived above integral points. And that pulls back to an action on M universal by symplectomorphisms. Now you have to figure out, what does P do? And if you've worked with these diagrams enough, you know that it should act by this nodal slide and cut transfer. So what's happening is, okay, so now I've drawn a little miniature version of my B univ, or rather like a very truncated version. But what I can do is I consider a path. So this is where I have here. So I consider like kind of a family of symplectomorphisms where I pull this entire array sort of down. So these points all move down. And so as I'm doing this, each of my bases is symplectomorphic to the, sorry, each of my resulting almost toric vibration under the new bases is symplectomorphism, symplectomorphic to the first guy. So I get this family of symplectomorphisms between these symplectic manifolds. But now, okay, once I pull this guy down sort of all the way, so now this guy, this pink dot here, I've done them by colors, you can see. So the pink dot here goes all the way down to this part. and then I also sort of transfer the cuts. So previously my slits were, this guy's slits was going up, and now his slit is going to go down. Actually draw that. So once you do this cut transfer like this, you're going to see a shearing. In this diagram, you'll see a shearing on the left-hand side. But once you've done that, well, okay, but now you're back to, there's a clear map between like the new manifold here and the one you started with. So that's G, that just does the obvious identification. And so you say P hat. So the mere symplectomorphism to P just acts by the composition of this time one symplectomorphism and G. So that's P hat. And then you're done. I mean, you need to check that the relations hold, but that's how these two generators act on your in universal. Questions on that? Okay, I have 3 minutes, so I want to actually get to the example because it's sort of one instance of where this machinery actually sees some of its power. So the example is this Markov cubic YD, where I've blown up P2 twice I've blown up P2 twice at the distinguished points on each of my lines at infinity. So that's indicated by this diagram here. And by work of El-Houthi and Cantalare, we know that the automorphisms of U, so the complement of D and Y, are quite large. And in particular, they have it admits as a subgroup this Z mod 2Z free product with itself 3 times. And this is a finite index subgroup. So you have some interesting complex dynamics here. Actually, does anyone want to guess the generators for these Z mod 2s? Okay, so it's a fun problem. So I'm sorry, like I have to sort of cut out the guessing like quickly because I do want to actually finish the talk on time. But what these things are generated by is you so this is a cubic surface. So you have YD. Okay. So it maps into P3. The whole thing doesn't actually map into P3. You'd end up with some singularity you'd have to resolve. So it's maps rationally into P3 as a cubic surface sitting in P3, and then you reflect across each of the corners of your triangle of lines. So you say like, so I've labeled these lines like R, Y, like Y. Sorry, I've labeled these intersection points Y, Z, X, and so I have these generators like Y, R sub Y, of like maybe Z is going to be equal to Z prime, such that Y Z prime are collinear. So you send it to the other collinear point and call that a reflection. So obviously that's order 2. And that actually ends up extending to an automorphism of your open U. And we can see this in our we can realize these as some group of automorphisms of the space fibering above this integral affine base. By it turns out if you factorize these reflections, you get that first you perform P squared, and then you map by this matrix 1, 0, 0, -1. So this just flips the sign of Y, and on these sort of base diagrams like this. Okay, so you do P squared, so you pull these 2 points down like that, and that moves that right up, right? And But now the point is that if I was actually going to do this like as a biholomorphism, I would have needed this divisor here, this gold divisor, to perform p squared. So I would need to have blown up another time on my YD to get this divisor here where I can or if you like to, you want to think about this p maybe as like in terms of like, okay, well, you have some fibration and you have some fiber with self intersection -1 and some exceptional hanging outfit, and you want to obtain a new fibration where you're flipping the exceptional in the fiber. But in order to do that, to get that description, you need to have this divisor. Sorry, none of that was making sense unless you've already thought about that. And then after you've done that, then you can act by this matrix here, and end up back at some cubic surface. But again, now you have a new divisor hanging off here. So the point is that in order to actually perform each of these birational transformations, or each of these automorphisms of your U, you might have to sort of blow up points on your original YD. And now I'm 2 minutes over, so I apologize, and I'll stop there.
Okay, let's thank Abigail. Okay, any questions from the room?
Can we come back to this sym L?
Yeah, sorry, let me so the question was to go back to this L thing?
Yeah, I think this is in your main theorem.
The main theorem, yeah. Right, so this thing here, right? Right?
Yeah.
Yeah, so the quickest way to think about this, I think, is say, if you think about this universal as some limit of Weinstein domains, then one way you can construct a symplectomorphism of the universal is sort of constructing maps between the subdomains. Sort of compatibly, right? So if I want to construct a symplectomorphism of this universal, then one way to do sort of map between the subdomains that form the direct limit and in a compatible way. So compatibly with the inclusions. And now what you want to say is, in order to make sure that I have a well-defined action on my Fukaya category, on my RAP Fukaya category. So let me actually do this. So I can say, I mean, in some sense, this might be how I want to define it. Like I'm going to say the RAP Fukaya category of M-univ is equal to, okay, and now I'm going to really screw up whether it's a direct limit or inverse limit, but it's, I think it's an inverse limit. Because I had, yeah, under Viterbo restriction. Is the inverse limit of the wrapped Fukaya categories of the MCs. And I know that if I have say a symplectomorphism I've constructed in this way of sort of a system of symplectomorphisms, that I'm going to get maps between my RAP Fukaya categories of the subdomains like this, so that you see an actual action on this, the inverse limit, then I might want to preserve some Weinstein structure at infinity. So you could have written this with a W. At some point, I think Oleg Lazarev convinced me that really all you want to kind of worry about is preserving the Liouville structures of each of the subdomains. So this L is sort of supposed to indicate that this inverse system of symplectomorphisms preserves the is a symplectomorphisms of Liouville domains on each of the sort of finite steps.
Can I ask a related question then? I'm ignorant on this non-finite Weinstein level, but is this limit definition the standard one, or is it? I thought this is not.
Sorry, say again.
So this new thing you wrote, that category of universal is. So is this the definition you take, or is it a property, or?
That's sort of a philosophical question. I think this is probably our definition.
Because I thought people were trying to define the left-hand side and try to show this. Anyway, so if you take this as a definition, yeah.
I think we should take. I think this is how I would take this as a definition. Sorry, I would take this as a definition. I think. I would take this as a definition, and I think at least Shilganatra also agrees with me. So that's sort of just an appeal to authority. But right, I guess you could also say, well, if I actually, I mean, it's kind of it's not hard to figure out what the Lagrangians you have a notion of Lagrangian for M units because you have an honest description as a symplectic manifold. The question is really like making sure you can define a Rapp-Fukaya category, and for that I would take this to be the limit. And so then you would say, well, the objects in my Rapp-Fukaya category are going to be if you like honest Lagrangians in my universal, but such that they restrict to like admissible Lagrangians under Viterbo restriction for each of my my restrictions to my subdomains.
Okay, yeah. Thanks. Any question from the room? Any more questions? Okay. Any question from the Zoom room? Okay, then let's thank Abigail again.